In the last module, we came up with third order equation, differential equation, which looks like this, and we said this is obtained by manipulation of the equation that was derived in the previous module. This was the ODE which was derived, and if I just clean it up a little bit by by dividing by this quantity on the right hand side throughout and grouping the terms, I get something like this. This transforms to this one, and the boundary conditions, which are these three given here, I have just written it here. So, on paper this looks like a ordinary differential equation. Well, it is an ordinary differential equation if and only if beta 1 and beta 2 and also the boundary condition which we have derived here, third boundary condition z of 0, which has this. None of these, please note, this equation which has been derived will admit similarity, is strictly going to admit similarity, meaning z is going to be a function of eta bar only, and any dependency on x and y should be completely lost, because even if beta 1, beta 2 or this one has an x or y dependency, you have no control over those and eta. Eta bar is something which we have now created such that this eta bar takes care of the variation of x and y. If you continue to have x and y in some form, some hidden form, may not be obvious, but in some hidden form, then you have not lost the dependency in x and y. So, what we are trying to say is this ODE in reality would amenable to similarity solution if and only if any x and y dependency in beta 1, beta 2 and any of the boundary conditions. Luckily, these two boundary conditions are just numbers 0 and 1, but the third boundary condition is having an expression which is a function of x. None of these should be a function of x or y rather. Therefore, this equation, slide number 9, this equation z triple prime plus beta 1 z double prime plus beta 2 1 minus z prime squared equal to 0 will admit similarity. Beta 1 and beta 2 and all the boundary conditions. What are the three boundary conditions? Z prime of 0 is something, z prime of infinity is something, z of 0 is minus Vw of x divided by dn of x. This is 1, this is 0. These two are not an issue. This one, beta 1 and beta 2, must not x or y, x and y, x or y, then only this equation will be amenable to similarity solution. This is the big, what you say, constraint here. So, not all situations will be amenable to similarity solution. So, beta 1, beta 2 and this one must be a constant. So, beta 1 is constant, beta 2 another constant and z of 0 a third constant. Constant 1, constant 2, constant. Only then will this equation admit similarity solution. Otherwise, it is not going to work. So, let us now do some manipulation. Let us consider 2 beta 1 minus beta 2. So, we are just going to write this. So, beta 1 we defined here. So, 2 beta 1 minus beta 2 we are just going to write. So, 2n by nu u infinity dn by dx minus beta 2 is n squared by nu u infinity squared du infinity by dx. What is this? This, if you closely look, it comes out to be, expand the bracket and see, you will get this. Beta 1 had to be a constant, beta 2 had to be a constant. So, this whole thing has to be a constant. So, I am saying 2 beta 1 minus beta 2, 2 beta 1 minus beta 2 is nothing but d by dx of n squared nu u infinity. So, integrate with respect to x from 0 to some arbitrary x. What can I say? N squared by nu u infinity evaluated between 0 and x will just give me n squared minus u infinity, because at 0 this whole thing is going to be 0. Right hand side, 2 beta 1 minus beta 2 into simply x. Therefore, n is nothing but nu u infinity 2 beta 1 minus beta 2 into x under root. We never told what this n was. Now, we are going to give it an expression. Let us keep this in mind. Okay, let us just keep this here and let us multiply this. This is slide number 10. You had n squared by nu u infinity is equal to 2 beta 1 minus beta 2 into x. Multiply by 1 by u infinity du infinity by dx both sides. So, I get 1 by u infinity n squared by nu u infinity du infinity by dx is equal to 2 beta 1 minus beta 2 divided by u infinity du infinity by dx into x. What is this quantity? This quantity was my definition of beta 2, n squared nu u infinity squared du infinity by dx. So, this is nothing but beta 2. So, therefore, I can write implies beta 2 is equal to 2 beta 1 minus beta 2 by u infinity du infinity by dx. This is x here. So, I just separate the variables. I can write beta 2 by 2 beta 1 minus beta 2 dx by x is equal to du infinity by u infinity. This manipulation. Now, I integrate and apply the limits. So, I integrate and apply the limits. I will get log of u infinity is equal to beta 2 by 2 beta 1 minus beta 2 times c log x. The constants, instead of adding, you are just taking it inside here, that is all, which means u infinity is equal to c x to the power beta 2 over 2 beta 1 minus beta 2. Okay. This form, this beta 2 over 2 beta 1 minus beta 2 we will call as m. And just let us go back to the definitions. What is m? It is 2 beta 1 and beta 2. What is beta 2? It has du infinity by dx. Where did this du infinity by dx come from? It came from dp by dx form, correct? So, if you go back to the history of where we started, dp by dx was related to du infinity by dx, which was then related to beta 2, which is now related to m. So, can we say this m is called as the pressure gradient parameter, because the pressure gradient is directly related to this m. dP by dx equal to 0, you will have a different value of m. dP by dx is negative, one other value. dP by dx is positive, some other value. So, this m is called as the pressure gradient parameter. Therefore, u infinity is equal to Cx to the power m. This profile, for this profile only, similarity solution is possible. What is this? What is so great about this? We will see in a minute. Remember, just let us go back to definition. We showed here n, definition of n is nu u infinity, this one. So, psi is equal to z of eta bar n of x. I will just substitute for n. Z of eta bar nu u infinity 2 beta 1 minus beta 2 into x. Therefore, my z of 0, third boundary condition for Vw, no, remember that? That is Vw of x with a negative sign divided by dn by dx is equal to constant. Okay, this is also constant. N we saw, this n differential we will take here, and that also has to be a constant. So, now we are going to say we had beta 1, beta 2 as some arbitrary constants. Why keep both of them arbitrary? So, let us choose, let beta 1 is equal to 1 and beta 2 is some general beta. This is as good as keeping both of them constant. So, I will choose beta 1 equal to 1 and beta 2 as any general beta. So, keeping this in mind, my ODE therefore becomes, I substitute beta 1 is 1, beta 2 is beta, therefore, transformed ODE. Slide 9, from there I am writing z triple prime plus z double prime plus beta 1 minus z prime whole squared equal to 0. This coupled with the other conditions, boundary conditions, z prime of 0 is the first boundary condition 0, z prime of infinity is the second boundary condition, z prime of infinity is the second boundary condition is 1, third boundary condition we just wrote, z of 0 is minus Vw by dn by dx is equal to constant. This is my ordinary differential equation. Now, everybody will be able to appreciate that this equation can be solved nicely. What is beta here? We have not written this beta now again in terms of m, the pressure gradient parameter. So, we said m is equal to, that we wrote here, m is equal to beta 2 divided by 2 beta 1 minus beta 2. We chose beta 2 as 1 and beta 1 as 2. So, m is equal to beta minus beta over 2 minus beta. So, we got m, therefore, 2m minus beta m is equal to beta, 2m is equal to beta into 1 plus m. Therefore, I get beta is equal to 2m over m plus 1. This is also something which might be useful. This is m, this is beta. Okay. Now, let us go back to where we were. This now you will be able to appreciate. When I put beta 2 is equal to beta, I am coming back to this. Pressure gradient directly related to m. Pressure gradient directly related to m, and therefore, m is called as a pressure gradient parameter. This important result helps us say that a family of solutions are possible for this case, that is this is a case of a wedge flow. Wedge is something which looks like this, something which can be shown like this. You have one, it's like a V which is tilted and the flow is coming this way. So, this is the solid and the flow is coming this way, and the central angle is pi times beta. 0 less than or equal to beta less than or equal to 1. When 0 equal to beta, you would get flat plate. When beta equal to 1, this angle would be pi, you would get what is called as, this is the flat plate solution, beta equal to 0. Stagnation point flow, where the jet comes and hits here, beta equal to 1 case, and then any angle beta would give rise to different solutions. When beta is less than minus 0.2, this is corresponding to a wedge which is like this. This is the case of flow separation. Okay, so entire family of flow situations can be solved by solving this differential equation with different values of beta. Flat plate that you will study or you will teach in an undergrad curriculum is where you have dp by dx equal to 0, beta equal to 0 or m equal to 0. That is one very special case. So, m equal to 0 implies u infinity is Cx to the power 0, which is constant. This represents the flat plate. U is equal to constant. This means du infinity by dx equal to 0, dp by dx equal to 0. These are all consequences of flow over a flat plate, right. Therefore, my Navier-Stokes equation becomes u du by dx plus v du by dy is equal to nu d squared u by dy squared. Or if I put this one beta as 2m over m plus 1, 2m over m plus 1, I would when m is equal to 0, you get the case of a flat plate, and your ordinary differential equation, which was something like this, would transform to something more simple. So, dp by dx equal to 0, which is flat plate, 0 pressure gradient, dp by dx less than 0, favorable pressure gradient. That means along the flow direction, pressure has to decrease. So, this is called favorable pressure gradient. This is what is needed. So, pressure decreases along the flow, it is called favorable pressure gradient. This is possible when beta is greater than 0. dp by dx greater than 0 is called adverse pressure gradient. Something is, pressure is increasing along the flow direction, the flow is getting retarded, therefore, the flow will ultimately separate, it will come out of contact with the solid surface. So, this is called adverse pressure gradient, dp by dx greater than 0, and this occurs for beta less than 0 and beta less than minus 0.2 onwards. So, minus 0.21, minus 0.22, so on and so forth. Any values which is lower than minus 0.2, the flow will separate out. So, this is something which you can give students an overall perspective. This is not directly related to flow over a flat plate, but you can give this to them. And now we have this 2 minus beta etc. sticking everywhere. So, we will just do a little bit of cleaning up and write the equation in a form we like. So, recall z of eta bar is u over u infinity. Let us call this now f of eta, f prime of eta. This is a new definition where we are going to clean up this eta bar to eta and a factor of 2 minus beta will come. So, let eta is under root 2 minus beta into eta bar. This has only for mathematical simplicity. This is only for mathematical simplicity. Therefore, z double prime is equal to d by d eta bar of f of this. Correct? Second derivative is same as second derivative of this, just that this is with a new variable. So, I will write this as df prime of eta d eta d eta divided by d eta bar, because this is only related this way, which gives me differentiation of this will give me under root 2 minus beta df prime of eta divided by d eta. So, what does this tell me? Z double prime is 2 minus beta under root f double prime. Remember, z double prime is with variable eta bar, f is with variable eta. This is the transformation which we need to keep in mind. And this you do the third derivative, z triple prime, another 2 minus beta under root will come. So, you will get 2 minus beta under root times 2 minus beta under root. So, you will get regular 2 minus beta f triple prime. So, we need f of eta from z of eta. Why do we need f of eta? Because my third boundary condition which is there, my third boundary condition which was z of 0, velocity boundary condition, y component velocity, z of 0 is needed. So, this z of 0 has to be coming from now f of 0. So, for that let us look at f of eta is equal to integral f prime of eta d eta, which is nothing but integral z prime of eta bar. I am just transforming it because these two are the same. I am replacing f prime by z prime eta bar. This I want to make as eta bar differential. So, I will have this under root 2 minus beta d eta bar. So, this is nothing but 2 minus beta under root z prime of eta bar d eta bar. Okay. Therefore, what is this integral? This integral is nothing but z of eta bar. Therefore, f of eta is under root 2 minus beta into z of eta bar. Therefore, z of eta bar, wherever you have z of eta bar, please replace it by this one. Therefore, third boundary condition also gets simplified in terms of f of this. So, substitute for z of eta bar, z prime of eta bar, z double prime of eta bar and z triple prime of eta bar. Wherever you have those, replace it with f of eta, f prime of eta, f double prime of eta, f triple prime of eta. Once I do this transformation, I will get a simplified ordinary differential equation which looks a little nicer. You please do the maths here and you will get an ordinary differential equation which looks nice. So, on simplification, 3 or 4 steps of algebra, we get f triple prime plus m plus 1 by 2. We are substituting for beta there. So, what was my beta? My beta was written in terms of m here, beta was written in terms of n as 2m by m plus 1. You substitute for beta and simplify, you would get f double prime plus m into 1 minus f prime squared equal to 0, subject to 3 boundary conditions which are similar, except that now you would treat them with f. When m equal to 0, you get flat plate. So, your ODE becomes f triple prime plus half f double prime equal to 0. This is what you will see in textbooks and this is what Blasius has solved for us. This is your ordinary differential equation. Okay. So, this is something which we need to keep in mind. We need to say to the students that this is not transformed just like that. The similarity variable which is not come from air, it is a very well mathematically thought of thing, and based on this you get the ordinary differential equation like this. U infinity is C x to the power m, n of x is nu u infinity 2 minus beta into x. We will write this nu C x to the power m 2 minus beta to the into x. This n of x would come out to be nu C 2 minus beta into x m plus 1 by 2. We can write dn by dx from here. We can write dn by dx from here, and then we can say eta is equal to y u infinity by nu x. This would come out to be y under root c by nu x to the power m minus 1 by 2. Okay. So, these manipulations and then the solution of this ordinary differential equation, this one for flat plate will be this one. We will show this and then go to the energy equation, which will be converted into an ordinary differential equation. We have taken care of u and v. So, energy equation has u dt by dx, v dt by dy. So, we have taken care of u and v already. We just have to transform the t. We will transform the energy equation, do the algebra, come up with the ODE for the energy equation, apply boundary conditions and show you the similarity solution. This will be done in the next couple of modules. Thank you.